Now, I will start the third lecture of the 9th week of this course. In this lecture, I am going to talk about X-ray crystallography. Okay. So far, we have looked at powder X-ray diffraction and we have looked at how to analyze the diffraction patterns. Okay. Now, X-ray crystallography is the most advanced method for determining the structure of compounds. Okay. And in X-ray crystallography, you not only determine the crystal structure, but you also determine the location of each and every atom in the crystal. Okay. And in order to do this, you need a very accurate instrument, a fairly sophisticated instrument that can accurately give you all the important peaks in the diffraction pattern. Okay. So, week 9 lecture 3 will be about X-ray crystallography, and let me also mention that lot of this is highly automated. Okay. So, I will just give a general overview of some of the concepts related to X-ray crystallography. Okay. So, the general philosophy of chemical analysis of crystalline compounds is the following, that when you say you want to identify a crystalline compound or you want to analyze it, okay, then what are the things that you need to do? So, the first thing you need to know is what is the composition of the compound. Okay, you need to know what it is composed of, what are the elements in it, what are the if there are some important organic functional groups, what are they. Okay. And typically for this you can use the usual spectroscopic methods. So, usual spectroscopic methods are used like UV, visible, IR, NMR, etc. IR, NMR, etc. You can use mass spectrometry and so on. So, there are several such techniques. Now, but for crystalline compounds, in addition to the composition, we also need to know the structure, the crystal structure. Okay. And the structure, when we say structure, we mean several things. Okay. So, you mean the crystal structure, that is what is the unit cell. Okay, what is the unit cell? What are the parameters of the unit cell? What are A, B, C, alpha, beta, gamma of the unit cell? Okay. Then you need to know within the unit cell are there the presence of defects or impurities or color centers and so on. Okay, as we know that I mean we already saw when we were discussing defects and impurities that small amount of certain impurities can give a completely different color to materials. So, these are related to the local structure and again these can also be determined using the spectroscopy methods. Whereas, the overall crystal structure determination is usually by XRD. Okay. Then you could also ask what is the structure on a larger scale. Okay. So, for example, the grains, what are the sizes of the grains, the microstructure. You could ask about the surface structure. So, what I want to emphasize is that you need several methods. Okay, you need several different methods to determine these. So, several methods are needed. and I won't list all the methods that are needed, okay, but I will just say that for example, if you want to determine the surface structure, you might use microscopy like SEM. For grains microstructure, you might use again SEM, TEM, etc. These are we'll talk about all these microscopic techniques. This is scanning electron microscopy, transmission electron microscopy. You can also use scanning tunneling microscopy, STM. Okay. Again, I don't I'll come back to all these as we go along. Okay. Now, coming to X-ray crystallography. Okay, so this refers to the determination of exact structure from X-ray. X-ray, it's essentially X-ray diffraction analysis. Okay, so this is what is meant by X-ray crystallography, and this is one of the most accurate and most reliable methods that is used. Okay, now we need to know what kind of what is the general framework of this X-ray crystallography. Okay, so if you want to determine the crystal structure, what you need to do is you from the X-ray diffraction pattern. Okay, so you measure f of f observed, okay, the structure factor, the form factor, okay, and then you try to construct some model for, and then from that you calculate this f of HKL, okay, and you try to look at the observed structure factor minus the calculated structure factor, okay, and you try to minimize this difference, try to make this difference as small as possible, so that you say that whatever you calculated is what is observed, and then you conclude what is the structure. Okay. Now, so clearly, as we had already seen that you need that there are a lot of things to be determined. Okay. So, if you have to determine H, K, L, A, B, C, and then you have to determine the coordinates of all the atoms in the crystal, all the atoms within the unit cell. So you need H, K, L, A, B, C, and alpha, beta, gamma. So, these are the unit cell parameters and coordinates of atoms in unit cell. Okay. Now, if you have a simple compound, okay, and let us say you have an idea that you have some idea of about the structure. Let us say for example, if you have an MX2, okay, X is some other element. Okay, so if you have a compound like MX2, like let us say it can be calcium fluoride. Okay, so then you need to know, as we said, that there are a lot of things that we need, there are several parameters, and usually it turns out to be only about only a few parameters that need to be determined. So, about 5 parameters, 5 variables. Okay. So, what I mean is that you might know you might have some idea about the crystal structure. So, you might know that it is cubic. Let us say if you know that it is cubic, then you only have one constant, that is A, to be determined. Okay. And further, but you also have to determine the location of the atoms, the coordinates of the atoms. So, typically about of the order of 5, I mean maybe 3, 4, 5, 6, something like that. Okay. Now, what I want to emphasize is that if you want to determine so many variables, then you need 10 to 20 peak locations. Okay. You need the 2 theta value from about 10 to 20 peaks in order to do this, and this can be done using powder XRD. So, powder XRD is fine. A usual laboratory scale powder XRD works. Now, on the other hand, if you have a more complicated compound, okay, for example, let us say you have something like YBaCO3O7. Okay. Now, this is a perovskite structure. Okay. It's actually a distorted perovskite. So, this typically has about you have lot of atoms. Okay. So, typically you can see that there are 7 plus 3 10 plus 2 12 atoms. Okay. And you will typically have about 15 variables to determine, okay, in order to determine the structure completely. Okay. And if you have 15 variables, okay, typically you need about in order to determine this 15 20 variables, you need about 100 to 200 intensities. You need to know about 100 to 200 intensities. Always what is done is you match it with several peaks and then you try to fit them. Okay. So always the experimental data is lot larger than the number of variables, and this is done in order to get accurate values of these variables. Okay. Now, for this you will typically use a single crystal XRD. So, you make a single crystal and then you put it in the XRD X-ray diffraction instrument. Okay. And because it is a single crystal, you will have to rotate it. Okay. But when this is done, you will get a very good intensity of all the peaks. Okay. So, this gives much higher intensity, and so you will be able to record several more intensities. Okay. Now, a more complicated case would be something like a biomolecule. Let us say or you could have a zeolite protein. Okay. And in this case you could easily have 100 or more variables, 100 to 1000 variables. Okay. And you would require something like 5000 to 50,000 intensities. Okay. And here you have to use a synchrotron source. Plus single crystal. crystal XRD. So, you have to use a single crystal X-ray diffractometer, but you have to use a synchrotron source of X-ray radiations. Okay. So, the intensity is very large, okay, and you can detect lot of peaks. Okay. So, now the question is the following, that you have, if you finish indexing the peaks, okay. So, suppose you have f of HKL, okay, and you know the HKL and you have identified, so peaks have been indexed. Okay, so you know all the f of HKL. Okay, so you know f of HKL for all HKL. All HKL. Okay. Now, how do you get the atomic coordinates? Okay, how do you get the atomic coordinates from this? You know HKL for, and you know the f of HKL. So, how do you get the atomic coordinates? Okay. Now, there is it's I mean this process is done using the following idea, that the electron, the f of HKL, okay, is related to the electron density okay, and this electron density field, that means the electron density at some coordinate, okay, u, v, w. So, this is some coordinate inside unit cell. That means, you imagine that you look at any point on the unit cell. So, u v w is some point inside the unit cell, and at each point there is an electron density. Okay. So, at each point in space inside the unit cell there is an electron density, and this electron density, if you know the electron density at all points in the unit cell, you can calculate f of HKL and vice versa. And the relation is the following. So, rho of u v w. So, this electron density is equal to 1 over v sum over h sum over k sum over L, okay, f of h k L times cosine, the cosine part of the Fourier transform, 2 pi h plus k plus L, h u plus k v plus L w. Okay. So, this is like the delta, okay, but the delta, the phase difference delta was only used for the phase difference delta was only used for location of the atoms, only for the position of the atoms, but this is at an arbitrary point within the unit cell. So, u v w is an arbitrary point within the unit cell, and this is actually what is called a Fourier transform, in fact, the cosine part of the Fourier transform. Okay. So, I will just write this, it is the cosine part of Fourier transform. Okay. And so the electron density is nothing but the cosine part of the Fourier transform of the structure factor. Okay. So, the structure factor, the geometric structure factor f of HKL, okay, the rho of u v w is the cosine part of the Fourier transform of f of HKL. Okay. So, now if you have this electron density everywhere, then you can make these electron density maps. So, for example, if you have if you look in a plane, if you look in one plane, okay, you can have these electron density maps, and these will typically appear as contour maps. Okay. So if you have something like this, if you have something like this contour maps. So, basically you can say that electron density is increasing as you go from the as you go from the outside to the inside of each of these. Okay. So, then immediately you would identify that an atom is located right here. These are the locations of the atoms, okay, where the electron density is maximum. Okay. And so, you can identify the location of the atoms using this electron density maps. So, electron density map can be used to identify atoms in unit cell. Okay. And this is again I should emphasize that this is completely automated. That means the instrument will do this for you. Okay. Will use some software to carry out this analysis and give you the electron density map. Okay. Now, one of the things about the electron density map is that you need to know the f of HKL with a sign. Okay. So, the f of HKL you need to know whether it is plus, positive or negative. Okay. But if you look at the X-ray diffraction pattern, then f of HKL, okay, you only see a positive sign of f of HKL. Okay. So, for this electron density map you need f of HKL with, and you need the information whether it is positive or negative. Okay. But often in this X-ray diffraction you only obtain absolute value of f of HKL. Okay. So, this is not sufficient to calculate rho, the electron density. Okay. And to overcome this problem, okay, there is something called a Patterson map that is made. Okay. So, the Patterson map uses the absolute value of HKL, okay, and it constructs a map electron. This is not exactly, this is not actually the electron density, but it is I will call it rho prime, okay, and it is constructed in exactly the same way, sum over H, sum over K, sum over L. And now, instead of f of HKL, I use the absolute value of f of HKL, okay, with a square, okay, and cos 2 pi H u plus k w k v plus L w. Okay. So, it is exactly like what was used in the case of the electron density maps, but it takes into account the fact that experimentally we only determine the absolute value of f of HKL and not f of HKL with its sign. Okay. And now this turns out, this Patterson map is related to location of pairs of atoms. Okay. So if you look at a Patterson map, okay, and if you look at peaks on the Patterson map, so just as the peaks in the electron density map were related to location of atoms, this is location of pairs of atoms. So basically the peak corresponds to a distance at which you find two atoms. So some separation between atoms. So okay, and then using some reference or some fixed atom, you can actually determine the entire crystal structure. Okay. Now, what I want to emphasize is that both this Patterson map and electron density map are also automated, okay, and these are parts of modern X-ray diffraction instruments. Okay. So, the single crystal XRD instruments, okay, which have either Patterson map or the electron density map, which can be calculated automatically. So all you do is you put your sample in, record the spectrum, and then analyze, and then you send it for analysis. Okay. So the spectrum is analyzed by the instrumental software, and then you get the entire electron density map at the end of it. Okay. So with this I will conclude this lecture. So this is the third lecture of week 9. Okay. In the next lecture I will talk about microscopy techniques. In fact, electron microscopy is again a very powerful technique to analyze crystals. Okay. And that will be with that we will conclude week 9. Okay. So the fifth lecture will as usual be reserved for practice problems and review of the contents of week 9. Thank you.